Okay, so here is our notes on light. So you're going to first go into your classroom and we're going to start here. It's going to be Unit 3. So if you can see, you have your topics over here on the right. So you want to click on Unit 3. Okay, and you're going to see a few more than what you see. But if you click on Unit 3, you'll see this first assignment, homework light notes. That's where we're going to be working. And you're watching this video, but also make sure that you've got your Google Docs open with your light notes for your Cornell notes, and make sure you're putting topic in as light notes, and then we'll do your essential question in just a second. Okay, so let's get started. Okay. All right, so we're going to talk about light, and we're going to talk about light with electrons. So I want you to keep in mind as we're talking about light, about electrons and how they orbit the nucleus and how you have the rings, but also now we're going to equate those rings to energy levels. So energy levels get higher as the number gets higher. So 1 is lower than 2, or 2 is higher than 1, 3 is higher than 2, 4 is higher than 3. So we're going to talk about how electrons move within those energy levels or rings and what happens. Okay. So our essential question is, what are the properties of light? So we're going to learn about how we measure light, what it looks like, what we talk about light, and then how we create it. So we're going to talk about all about light here. Okay. There's two camps, what we call two camps of thought about light and what it means. The first one we're going to talk about is light travels as waves, which is the first thought that they had many, many years ago. And the second thought that we've kind of started developing later on with Albert Einstein and so forth is that light travels as particles. So just like your particles that you saw in your solid, liquid, and gas, that light also has particle properties, that it can move around, that it can move fast, it can move slow, it has energy. Okay. All right, so our first camp of thought was that light travels as waves, and it started with Sir Isaac Newton, and he introduced the mathematics needed to first describe energy traveling as waves. We are not going to ask you about who thought of it or anything about Newton, but this is just to give you some history and some background. So Sir Isaac Newton, his first thought is that light, as you see it, travels as a wave. And he used some equations in math to explain it. You're not going to need to know those equations, okay? But it kind of describes how they move, okay? Okay. There's three primary characteristics of waves, and you're going to have to understand what these are and how they relate to each other. And we'll go through that here. The first one is wavelength, and it is designated by this delta sign. Okay, if you ever see this in an equation, you will not need to know any equations about waves. It is a delta, and it is the distance of one complete cycle. We'll see a picture of that in just a minute. The second characteristic I want you to focus on is frequency. And I know you think, gosh, it should be an F, but it's a V. It is what it is. Okay, and that is the number of cycles past a given point. And we'll see a picture of that. And the third characteristic we'll talk about is energy. How much many waves occur at a certain spot. So it should say how many waves occur at a certain spot. Okay. The higher the amount of waves in a certain area, the higher the energy. So let's look at a picture of those. So here we go. Okay. We see a crest, a trough, and an amplitude is how far it goes from the middle point. But a wavelength is from the middle of one wave to the middle of another. So how long that is between this wave and this wave. That is a wavelength. Frequency is, here's a snippet of one wave, and you can see it's 1, 2, 3, 4, 5, 6 boxes long, just like this one. And this is a high frequency, lots of waves within a given time. This is a low frequency, low amount of waves in the same frequency of time, in the same amount of time. We can also talk about energy. This has a high energy. It goes up and down, woo, 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 many, many times, up and down, up and down, up and down. It has a very high amount of energy. This has a low amount of energy. Look at how many waves we have in that given time. It's very slow. It moves very just kind of calm. So this is a low energy and a low frequency and a high energy, high frequency. And we're going to talk about the relationships between them. So you can tell that frequency and energy have what we call a direct relationship, which means they match. If it's a high frequency, it's a high energy. If it's a low frequency, it's a low energy. And we'll look at a slide in just a minute. But how wavelength is completely opposite of that. That you can see the wavelength is very short here from one crest to the next, but very high here, okay? So in a low frequency, we have a high wavelength, and in a high frequency, we have a low wavelength. So they are what we call an indirect relationship. And that's what we talk about here. So these are definitely relationships you will need to understand and how they work together. So wavelength and frequency have an indirect relationship, which means they're opposites. Okay, if wavelength is high, frequency is low. If frequency is high, wavelength is low. Frequency and energy have a direct relationship. So they match. If one is high, the other is high. If one is low, the other is low. And then wavelength and energy also have an indirect relationship. So they are opposite. When wavelength is high, energy is low. And when wavelength is low, energy is high. So they are indirect. These are relationships you definitely need to have in your notes. All right, let's talk about our second camp of thought, that light travels as a particle. And this was started by a scientist called Max Planck. Sometimes he is quoted as the greatest mind of all time. And he said that energy had to be more than just waves. There had to be more characteristics of energy and light other than just waves. So his thought was this, that light travels as particles and that energy could only be absorbed in fixed quantities. And that's just a definition of quantize. You will not need to know the definition, but if you hear me say quantize, I wanted you to know what it means. So the analogy is that it's climbing a ladder. And actually in a minute, you'll learn that it's climbing as we get through this, that it's like electrons are climbing a ladder. So increasing energy is we go higher up, okay? So as the wave or the light has more energy, okay, we're going up in energy levels, okay? So it's like you have ground, and we'll talk about electrons and ground state, and then there's excited state. So there's different energy levels. Remember, those Bohr rings are also energy levels. So as you go up in the rings, we're increasing in energy, okay? As we go up all the way to the seventh ring. The seventh ring of a Bohr model, where an electron is the highest energy. It has those electrons have the highest energy of all of them, okay? But we can give these numbers. We can give them quantities. We can give them something like a particle, okay, of energy. So electrons moving energy levels are going up or down the ladder. There's two definitions I need you to understand and get. The first one is an excited state. And that's where electrons absorb energy. They move up the ladder to the higher energy levels and move to a higher state of energy up the ladder. Then we have what we call their ground state. Electrons release energy and move back to their original state of energy. They go down the ladder. That is when we get a release of what we call a photon. That is a particle of light. We call it a photon, and light is seen. So it's happening in front of your eyes right now. So what does that mean? That means, say, hydrogen. If we have hydrogen in the air, it has that one electron on the first ring, okay? It can jump to a higher energy level, even though it doesn't have those rings, but it can jump, and it can go up to, say, 2. It can absorb the energy to get up there, but it doesn't stay for long, and it releases that energy because it gets so excited. It's kind of like if you drink a Red Bull. It only lasts for so long, or you eat a whole bag of candy. That energy only lasts for so long. So then it crashes back down to this ground state, releasing that energy as a photon, and that's when we see light. Okay. So a couple other things to talk about as some words as we start talking. Energy is quantized, so there are specific amounts, and we'll learn what those, we call them nanometers, and you're going to learn different visible colors of light have a certain number with a unit. So we call that it's quantized. So the amount of energy to move an electron from one energy to another. There is a certain amount of energy that electrons need to go from energy level 1 to 2, or 1 to 3, or 1 to 4. Whatever that happens, or 2 to 3, or 3 to 4, there's a certain amount of energy that electron has to absorb to get there, okay? So quantum amount, those are the packets of energy needed to come out. So those quantum amounts, and you're not going to be tested on all these things, but quantum amount, if you hear me say it, it's the amount of energy that electron needs to absorb to go from, say, energy level 1 to 2, or 2 to 3, okay? That is a quantum amount. And energy now has particle properties, so it can move just like a solid particle, a gas particle, or a liquid particle. You saw that they absorbed energy, okay, from the heat when you heated them, and they started moving faster. And they started taking on and moving around and causing different things. Same thing with electrons and light, okay, that they can absorb energy. And it has to be a particle to do that, okay? And of course, I say here, energy is required to change a phase. Energy is required to change in a phase from a solid liquid to a gas. Energy is also required for electrons to create light, or photons, okay? The other thing we talk about as light travels as particles is the higher the frequency, the greater the energy. We just talked about how they have a direct relationship. So the higher the frequency, the higher the nanometers that we can measure, the greater energy that light has. And you'll see in a minute that the greater that energy that light has, the more dangerous it is to you. And particles of light are called photons. We call them photons. All right, so one of the scientists that really kind of developed this whole idea that light travels as particles was Albert Einstein. And he proposed that the electromagnetic spectrum is quantized. What does that mean? It has numbers. We can measure it, okay? And the electromagnetic spectrum is all the way from visible light to magnetic light, okay? And the electromagnetic spectrum can show us two things, okay? When we'll look at the spectrum in just a minute, but it describes how energy travels. So these are very important concepts here, a red shift and a blue shift. And you'll see in a minute when you look at the picture, if our light, and we see red and blue, we see colors, we can't see outside that visible spectrum. But if we see a red shift, if we see more red light, you'll see in a minute, it's a shift to the visible red light, and that has longer wavelengths, okay? So remember that. And then if we say blue shift, that is a shift to the visible blue light, and those have shorter wavelengths. So we just talked about how wavelength is related to frequency and energy. Remember, they have an indirect relationship. So a longer or higher wavelengths will give me a low energy, low frequency, and shorter or higher wavelengths will give me a high energy, high frequency, okay? All right, so here's our electromagnetic spectrum, and it just has a portion of it blown up to visible light. This is what we're going to use, and you'll see we're going to use to see how far stars are away from us, too. We're going to use that in this unit to figure this out. But this is our electromagnetic spectrum, and you can see in wavelength in meters, okay? And this is our smallest wavelength, so our lowest, which means it's our highest energy. Highest frequency are gamma rays. These are the most dangerous of all of the light wavelengths, okay? X-rays, of course, we use lead to protect us from X-rays. Then ultraviolet rays, here's our visible light here. And then our less dangerous ones, we get to infrared rays, radar, FM, which is on, some of you may know it, on your radio in your car, the FM radio. TV, shortwave, and then AM is even a longer wavelength. So this is the whole entire electromagnetic spectrum. Unfortunately, we don't have the equipment here in class, so we really focus more on our visible light here, okay? All right, so the atomic spectra, what does that is kind of one thing we use, and I wish we could be here in class and do our atomic spectra light. I actually plug in different elements into a system that throws energy into it, and those light up at certain things, at certain colors. I then give you glasses, and you're able to put them on, and you can see the different levels of light. So you would see like a strip of purple, blue, green, yellow, red. Unfortunately, if you're here at Distance Learning or making this up, notes up, you won't be able to see this. But so every element has a unique atomic spectra. So they give off a certain amount of light, color of light. And that's because those electrons are at different levels. Remember, we learned that period 1 has 1, period 2 has 2, and each one has different number of electrons, and 3 has 3. And so you can see that as we get up to like 7, you can have those ones in energy level 1 or ring 1 jump all the way to 7, absorb that, and give off a really high, right? A really high frequency. So it could give off a gamma ray. So some of those ones at the bottom, and you'll see if you read through the periodic table, that's where you're going to find uranium. And you're going to find those elements, or radon. Those are those elements that are used in nuclear reactors. And that's because they have so many different energy levels that those electrons can really absorb those high, a lot of energy, and they put off these gamma rays, which are very dangerous, okay? So the more energy levels you have, the more those electrons can go, okay? But they can use these, the atomic spectra, the fact that each element gives off a certain amount, different types of colored light, that they can identify what is in something that is super far away. And you'll see this happen with stars. I'll show you how that works. So they can tell what elements are actually in a star just from the colors, the streams colored of light that we receive here on Earth. They can break that up, okay? So they can identify elements from their spectrum, okay, from what they give off. This is pretty much Einstein's discovery now, that he was able to give energy a mass, that's m, and this is a constant c squared. But he was able to take energy and give it a mass. So what else has mass? Well, particles have mass. And so that's where we can look, and that energy definitely has mass. I would have shown you if you were here in class the whole derivation of that equation, but Albert Einstein actually showed us that light has to have mass. Light has energy as a wave, but it also has a mass, and it has properties of a particle. Okay, so let's review. So elements absorb energy. That means they go to excited state. Do they give off light? No. So when they absorb the energy, remember, they are not giving off light. So when they go to the excited state, atoms get excited. Do they give off light? No, not yet. Electrons move to a higher energy state. They move to excited state. They're moving up to the excited state. Do they give off light? Not yet. Okay. Releases energy, excess energy, by emitting a photon bundle of light at various wavelengths to produce emission spectrum of the atom and return to ground state. Yes, that is when we give light. Okay, so when they absorb this energy, they are not giving light. They are taking it in, just like you're drinking a Red Bull. You're taking it in. Your energy is getting all up there in your body. And then you crash and you release it as you're going. It may take you an hour or so, but you then release it and you fall back down to your normal activity level. That is what atoms do, or electrons. But electrons do it super fast. It may take you an hour. It takes electrons nanoseconds, okay, to do this. They absorb that, go up in the energy levels, maybe to 7, and then release it and go back down, and boom, we get light. And depending on how much energy they have absorbed, we may get some dangerous waves of light, or we might just get some visible ones, okay? All right, so now what I want you to do is go back through and process your notes. So make sure you're highlighting any important information I may have given you. You're going to make connections to the notes in the left column and add any questions you may have for me in the left column. and then you're going to write a 3 to 5 sentence summary of your notes. So remember, to get credit on your notes, you need to make sure there's highlights and a summary and that you've taken notes. All right, well, that's the end of our light notes. Thank you very much.